Welcome back, everyone. Ready to dive deep again? This time we're tackling a subject that's both fundamental and mind-bogglingly vast. The universe and its tiniest building block.
The tiny holding up the vast, interesting way to put it.
We'll be drawing from a pretty hefty source for this deep dive, a university-level physics textbook. So buckle up for some serious insights.
We'll try to break down the complexities into something a little more digestible, though, don't worry.
Exactly. We're aiming to give you a solid grasp of concepts like nuclear physics, a bit of quantum mechanics, and even touch upon cosmology.
The big, the small, and everything in between.
Sounds like a plan. Let's get started, shall we? We're going to begin our journey with something we all know, at least in name, the atom. The very building block of, well, everything around us.
Familiar territory, but it's when we zoom into the heart of the atom, the nucleus, that things start to get really interesting.
Because packed in that tiny nucleus are protons and neutrons, right?
Right. And holding them together is one of the fundamental forces of nature. The strong force. It's this force that overcomes the repulsion you'd expect between all those positively charged protons crammed in there.
So it's a pretty powerful force, then, to keep them all bound together like that.
Powerful, yes, but also very short range. It acts over extremely tiny distances, essentially confined within the nucleus itself.
Huh. A very localized superpower, then.
Yeah.
So the number of protons in the nucleus, that determines what element we're dealing with.
That's the atomic number. But, and here's where it gets interesting, the number of neutrons can actually change.
That's where isotopes come in, right? Different versions of the same element.
Exactly. You've probably heard of carbon-14 dating, using a radioactive isotope of carbon to figure out the age of, say, fossils.
Yeah, it's amazing how scientists can use that to peek into the past like that. So carbon-14, 6 protons, 8 neutrons, and it's radioactive. What does that actually mean for an atom to be radioactive?
It means the nucleus is unstable. It undergoes decay, throws off radiation as it tries to become more stable. Each radioactive isotope has a specific half-life, the time it takes for half of it to decay.
And for carbon-14, that half-life is about 5,700 years, which makes it handy for dating things that are thousands of years old.
Exactly. It gives us a sort of clock to measure time on a geological and archaeological scale.
Pretty neat trick. But shifting gears a bit, when we talk about the nucleus, we can't avoid the elephant in the room, or rather, the famous equation in the textbook.
You're talking about Einstein's EMC-Prapi.
The one and only. It basically tells us that mass can be converted into energy, and a tiny bit of mass can release a whole lot of energy.
And that, of course, brings us to nuclear weapons, a pretty stark example of the power lurking within the nucleus.
Definitely a turning point in history, to say the least. And the science behind it is nuclear fission, right? Splitting a heavy nucleus like uranium.
Uranium-235 is the usual suspect, and what makes nuclear weapons so devastating is the chain reaction. Fission releases more neutrons, which trigger more fission, a cascade of energy release.
A runaway process. So harnessing that power, but in a controlled way, that's the idea behind nuclear reactors.
Yeah.
Generating electricity from fission.
Exactly. But control is key. We've seen with accidents like Chernobyl and 3 Mile Island what can happen when things go wrong.
A stark reminder of the risks involved. It seems like with nuclear power, we're always walking this tightrope between incredible potential and potential catastrophe.
A dilemma with no easy answers, that's for sure. But so far, our journey's been focused on the nucleus. Ready to explore the even stranger world of the electrons?
Let's do it. I'm curious to see where this deep dive takes us next.
Now, as we shift our focus from the nucleus to the realm of electrons, we enter a whole new ballgame. The quantum world.
Quantum mechanics. I have to admit, it's a bit intimidating. Like classical physics, the stuff that describes how planets move or how a ball flies through the air, that seems intuitive. But when we get down to electrons, it all goes out the window.
In a way, yeah. Classical physics works great for the big stuff, the macroscopic world. But when we're dealing with the tiny realm of electrons and other subatomic particles, it just doesn't cut it.
So what makes these tiny particles so different? Why do they play by a different set of rules?
It's a bit hard to wrap our heads around, but in the quantum world, things get fuzzy. We can't pin down an electron's position and its momentum with absolute certainty at the same time. Heisenberg's uncertainty principle.
So it's like we can know where it is or how fast it's going, but not both at once.
Exactly. And it's not a limitation of our instruments. It's a fundamental principle of the universe at that scale.
A bit unsettling that there's this inherent limit to what we can know. But it sounds like some pretty brilliant minds tackled this head-on. Planck, Bohr, Einstein, they all had a hand in this quantum revolution, right?
Absolutely. Max Planck kicked things off with his discovery of the quantum. It's a tiny packet of energy, showing that energy doesn't flow continuously, but in these discrete chunks, quantized.
Like little bundles of energy instead of a smooth stream. So how did that apply to the atom itself? How did that change your picture of it?
Well, Niels Bohr built on that idea. He proposed that electrons in an atom can only exist at specific energy levels. They can't just be anywhere around the nucleus, they have to be in these distinct orbits.
Ah, like those electron shells we learned about in chemistry. Different energy levels for the electrons. Okay, that's starting to make sense. But then there's Einstein and his work on light. How did that fit into this quantum picture?
Einstein's insight was that light, which we usually think of as a wave, can also act like a particle, the photon.
The wave-particle duality. That one still throws me for a loop. How can something be both a wave spread out in space and a particle existing at a specific point?
It's one of the big mysteries, and it challenges our intuition. But experiments, like the famous double-slit experiment, have confirmed it. Even a single photon can act like a wave, going through both slits at once.
So it's like the photon is in multiple places at the same time. My brain hurts a little trying to picture that.
Yeah.
But this quantum stuff, as abstract as it is, it's had some real-world impact, right? Like with electron microscopes.
Absolutely. Electron microscopes use the wave nature of electrons to achieve much higher resolution than we could ever get with light microscopes.
So they're using electrons as a kind of light to see things,
Yeah.
taking advantage of their wave-like behavior. Clever.
And with those powerful microscopes, we've been able to see things that were once invisible, like viruses.
Those tiny infectious agents that cause so much trouble. I always picture them as these little, almost mechanical-looking things.
They are fascinating structures, essentially genetic material, DNA or RNA wrapped in a protein code. They're like tiny hijackers taking over a cell's machinery to replicate themselves.
Not so tiny when they're making you sick. But okay, quantum mechanics. It explains the behavior of particles, helps us visualize tiny things. But there's even wilder stuff, right? Quantum computers, teleportation, that kind of stuff.
We're just scratching the surface here. Quantum mechanics has opened up possibilities that were once pure science fiction. Let's start with quantum computers. They're based on a key concept called superposition.
Superposition. If I remember correctly, that's the idea that a quantum particle can be in multiple states at once until we measure it.
Exactly. It's like imagine flipping a coin. While it's spinning in the air, it's both heads and tails at the same time.
Okay, I can kind of visualize that. So a quantum particle can be in a combination of states simultaneously. And that's how quantum computers work.
The basic unit of information in a quantum computer is a qubit. And unlike a regular bit, which can be 0 or 1, a qubit can be both 0 and 1 at the same time, thanks to superposition.
So they could explore multiple possibilities at once. That sounds incredibly powerful. But I imagine there are some pretty big hurdles to making that work in practice.
Oh, absolutely. One of the biggest challenges is maintaining this delicate superposition. Qubits are extremely sensitive to their environment. Any interaction can cause them to collapse into a single state, and poof, there goes the quantum advantage.
So isolating them, keeping them in this delicate quantum state, that's crucial. What about measuring these qubits? Doesn't that cause problems too?
That's another tricky part. When you measure a qubit, it forces it to choose. It collapses into a definite state, like our coin finally landing on heads or tails. We can't observe the superposition directly without destroying it.
It's like we can't peek behind the curtain without changing the show.
Yeah.
But even with all those challenges, quantum computers are being developed, right?
Oh, yeah. It's a rapidly advancing field with huge potential for fields like drug discovery, cryptography, material science. We're still in the early stages, but it's exciting to see what the future holds.
Speaking of mind-blowing possibilities, what about quantum entanglement? That's another one that always makes my head spin.
Entanglement is definitely one of the weirdest things in quantum mechanics. Basically, you can have two particles linked together no matter how far apart they are, measure the state of one, and instantly you know the state of the other.
Sounds like they're communicating faster than the speed of light, which isn't supposed to be possible, right?
It's one of those things that even Einstein struggled with. He called it spooky action at a distance. But experiments have shown again and again that entanglement is real.
So two particles, miles or even light years apart, are somehow connected in this instantaneous way. It's like they're part of some invisible web. But it's not just a theoretical curiosity, is it? There are actual applications being explored.
Oh, yes. Quantum entanglement has a lot of potential, especially for things like secure communication and, again, quantum computing. And there's also the idea of quantum teleportation, which always captures the imagination.
Teleportation, like beaming someone up, like in Star Trek? Sign me up.
Well, not quite that dramatic. Quantum teleportation is about transferring the quantum state of one particle to another at a distance. It's not teleporting the actual particle itself, but its information, its state.
So we're recreating something at a different location without physically moving it. It sounds like we're bending the rules of reality.
In a way, we are. Quantum teleportation is still in its early stages, but it's a fascinating area of research. The possibilities are truly mind-boggling. So we've gone from the nucleus, explored the quantum world. Are we ready to go even deeper?
Lead the way. I'm ready for the next level of this deep dive. From the quantum world, we now venture into a realm where scientists smash things together to figure out what they're made of. Particle physics.
It sounds a bit brutal, but it's how we unlock the secrets of the universe's most fundamental building blocks. We're talking extreme energies, incredible precision, amazing feats of engineering. Think particle accelerators like the Large Hadron Collider.
The LHC, yeah, I've seen pictures. It's this massive underground ring miles across. But why do we need something that big, that powerful, just to study tiny particles?
Well, to really see what these particles are made of, we need to smash them together at incredibly high speeds, close to the speed of light, actually. And that takes enormous energy. The LHC uses powerful magnets to accelerate these particles and then smash them head on.
And I'm guessing the debris from those collisions is what tells us something about the particles themselves.
Exactly. At those high energies, the collisions create conditions similar to the very early universe. Energy can transform into matter, creating a whole shower of new particles. It's like smashing a watch to see how the gears work, but on a subatomic level.
I like that analogy. So out of all this smashing and analyzing, we've come up with the standard model of particle physics.
Right. It's our current best understanding of the fundamental particles and forces that make up, well, everything. It's not a complete picture, but it's pretty impressive.
So break it down for me. What are these fundamental particles?
We have two main categories, quarks and leptons. You've already met quarks. They're what make up protons and neutrons.
Right, those particles in the nucleus. So quarks are even smaller than protons and neutrons.
Yep, and they have fractional electric charges. Unlike protons and electrons, which have whole number charges, quarks come in different flavors, up, down, charm, strange, top, bottom. Combinations of quarks form other particles called hadrons. Protons and neutrons are hadrons.
Okay, so quarks combine to form bigger particles. What about leptons? What are they all about?
Leptons are another fundamental type of particle. The most familiar one is the electron. But there are also heavier versions, the muon and the tau, and their corresponding neutrinos. Neutrinos are fascinating. They barely interact with anything. They can pass right through the Earth.
Ghostly little particles. So we have quarks and leptons, and they interact with each other through different forces.
Right. Exactly. The standard model incorporates three of the four fundamental forces. The strong force, that's what binds quarks together. The weak force, responsible for things like radioactive decay. And the electromagnetic force, the one that governs interactions between charged particles.
But what about the fourth force? Gravity. Doesn't it fit into this model?
That's the million-dollar question, or maybe the billion-dollar question. Gravity has been incredibly difficult to incorporate into the standard model. It's a big puzzle, and it's one of the main reasons why we know the standard model isn't the final answer.
So we have this model that explains a lot about the subatomic world, but it can't explain the force that governs the universe at the largest scales. Ironic, in a way. But speaking of the universe at large, let's shift gears again and talk cosmology.
Cosmology, the study of the universe as a whole, its origins, its evolution, its fate. And the leading theory for how it all began is, of course, the Big Bang.
The idea that everything started from a single point, incredibly hot and dense, and has been expanding ever since. It's mind-boggling to even try to picture that.
It's a challenging concept, but there's strong evidence to support it. One of the most convincing pieces is the cosmic microwave background radiation. It's a faint afterglow of the Big Bang, a kind of echo of that primordial event that we can still detect today.
So we can actually see remnants of the Big Bang, radiation that's been traveling through space for billions of years. That's incredible. What about the expansion itself? Is the universe still expanding?
It is, and in fact, observations show that the expansion is accelerating. That was a big surprise when it was discovered. It led to the idea of dark energy, a mysterious force that seems to be counteracting gravity, pushing everything apart at an ever-increasing rate.
Dark energy. Another cosmic puzzle to add to the list. It seems like the more we learn about the universe, the more we realize how much we don't know. But isn't that part of the excitement of science, that there's always more to discover?
Absolutely. Each discovery opens up new questions, new avenues to explore. And in our exploration of the cosmos, we encounter some truly fascinating objects. Neutron stars, for example. They're the remnants of massive stars that have exploded as supernovae.
Neutron stars, those are incredibly dense, right? I've heard that a teaspoonful of neutron star material would weigh billions of tons on Earth.
It's an almost unimaginable density, a testament to the extreme conditions that can exist in the universe. And even more extreme are black holes, regions where gravity is so strong that nothing, not even light, can escape.
Black holes, those cosmic vacuum cleaners that gobble up everything in their path. Sounds like science fiction, but they're real, aren't they?
They are.
Huh.
We can't see them directly, of course, but we can observe their effects on surrounding matter. They're the end result of the most massive stars collapsing in on themselves, creating a region where gravity reigns supreme, warping the fabric of space and time itself.
Well, we've covered a lot of ground in this deep dive. From the tiniest particles to the vastness of the universe, it's been quite a journey.
We've explored the building blocks of matter, the forces that govern their interactions, the evolution of the universe from its fiery beginnings to its mysterious future. It's a story that continues to unfold, full of wonder and still full of unanswered questions.
That's what makes it so fascinating, right? The pursuit of knowledge, the drive to understand the universe and our place in it. And on that note, we'll leave you with one final thought to ponder. If the universe began with a Big Bang, what existed before that singularity? Or is that even a question we can ask? Thank you for joining us on this incredible journey of discovery.
Until next time, keep exploring the universe within and around you.